geometry and process calculation. So in the previous lecture, I think that was lecture 8 or lecture 9. So I have discussed about the steady and unsteady state operation, or I mean overall material, how to write the basic equation or general equation for the material balance. So here this was the general equation for the material balance, where we have observed that there is a material input to the system. If we have a system where the material will in minus material output from the system, plus material generation within the system, minus material consumption within the system, that is equals to accumulation of the material. So we will solve lots of question on this kind of problem, but yes, this is the general and fundamental equation for the material balance for a particular system. And then I have also discussed about the steady and unsteady state process, where I have told you that in a steady state process, the process variable or the system variable like pressure, temperature, concentration or flow rate, that won't change with respect to the time. That's why this is called as the steady state process. And then I talked about the unsteady state process, where process variable like pressure, temperature, concentration, flow rate will vary with respect to the time. And then I have divided the material balance problem in two parts, where I have talked about the process involving no chemical reaction and the process involving the chemical reaction. And for both of these part, we will be understanding the steady state and unsteady state process. And after that, I have also described one simple example of unsteady state process for the differential distillation or simple distillation. This is also called as the release distillation, and we'll study these things in subsequent lecture, how to perform the material balance for that. But yes, this is a unsteady state operation, where I have told you that more volatile component in the concentration of more volatile component in the vapor phase will increase with time, and the concentration of less volatile component in the residue will increase with respect to the time. And that's why this is called as the unsteady state process. And when I talk about the batch and continuous process, in batch process I have told you there is no inlet and outlet. So basically you put a particular amount of material inside the system, and with respect to the time you will find there is a change in the concentration or pressure of particular reactant and product, and that's why this is called as the unsteady state process. So mostly you carry out the batch operation at the unsteady state condition. Then we talked about the continuous process, where I told you that a continuous process can be operated in both a steady state and unsteady state mode, where if we talk about the steady state mode, then inlet will be, or input will be equals to output. And if we talk about the unsteady state process, where input will not be equals to output. So after that also I have discussed about the basics of calculation, right? Now, in today's lecture, I'll be talking about. Let's imagine one fundamental thing to understand the motivation of this lecture today. So, imagine you are running a chemical plant and you need to produce a specific amount of product, right? So, you know what goes in and what comes out, but how do you figure out the exact quantities? So that's where the material balance and degree of freedom comes. So today I'll be talking about the independent material balance and the degree of freedom concept, and you'll understand this concept basically helps you to understand how many equations are required to solve these kind of material balance problem. So let's try to understand independent material balance equation. So degree of freedom concept is very important to understand, because most of the people don't understand these things. So I think what I remember in GATE 2025 or 24, there was a question from degree of freedom from process calculation. So in process calculation, people only understand the energy balance, material balance, and then goes to the examination. But it's not like that. They can ask question from the degree of freedom as well. So today what I'll do here, today we will learn how to determine whether a problem can be solved using the concept of degree of freedom, and how to apply it to the real process like distillation or some kind of evaporation. We'll see, right? So in any problem, what happens, we have in any problem if you are starting solving any problem, you will be having unknown variable, and the second will be equation to solve them. So basically, let's say we have two variables, ax plus by equals to c, and sorry, a1x plus b1y equals to c, and again a2x plus b2y equals to c1 and c2. So if I talk about the variables over here, we are supposed to solve a1 b1 or a2 b2, something like that. Is that clear? So in order to solve this equation, we require some so in order to solve this equation, let's say if you want to find out the constant a1 a2 b1 b2, something like that. So basically what happens, you solve this equation. Let's say if I make a matrix over here, a1 b1 a2 b2 and then xy, that is equals to c1 and c2. So you solve this equation and you calculate the value of constant. So you require some kind of equations to solve some variables or something like value of a1 b1 and a2 b2 here. Right. So the key question here is that do we do we have enough equation to solve the unknowns? That is very important thing, right? So the key question that arises here, the key question that we ask here, that do we have enough equation to solve the unknowns, right? So then there comes a degree of freedom concept. So we define degree of freedom, that is equals to unknowns minus independent equation you have. Right. So let's say how many independent equation you have written using the material balance, and how many unknowns are there in the in the problem, that is that can be defined using the degree of freedom. Now you have a degree of freedom. So now if we talk about, if degree of freedom is greater than 0, then the problem is solvable, right? You can solve the problem. If your degree of freedom, if degree of freedom equals to 0, then the problem is solvable. If degree of freedom is 0, then system needs more information. So you need more information to solve the problem. Need right. And if we talk about degree of freedom is less than 0, then too many equations there. There are too many equations, right? So you cannot solve. So in this particular case, you will be able to solve the the problem, right? That is very important to understand. So now next thing that arises here is, now how do we know the number of independent equations, right? So how do we know the number of independent equations? So in order to answer these things, first let's say if there is no chemical reaction, right? So if I'll talk about if there is no reaction, if no reaction is happening, then the number of independent equations can be written as number of component. And if there is reaction, right, If there is reaction, then number of atomic species will be there. Right, so you'll write the balance for atomic species, and then you have these things. So let's try to solve some problem where you will be able to understand how these things work. So let's apply the real, apply this concept to the real engineering problem, like azeotropic distillation. So there may be another examples also. Azeotropic distillation of ethanol and water system. So in azeotropic distillation, you require some extra component for distillation, and that extra component will be using benzene. Right. So how will we answer these things? So what we have seen here, there is component, right? You have ethanol, sorry, C2H5OH, right? You have water, and then you are using benzene as well. So the number of component that you can see in this problem, right? Now how many unknowns should be there? Will be 3, and then the number of equation, you can do the balance for all these 3, so number of equation will be 3. So what do you think the degree of freedom is? So if I calculate the degree of freedom, so I have told you number of unknowns, let's say, or number of components minus equation, that is equals to 3 minus 3, which is equals to 0. So you have 0 degree of freedom. That means this problem is solvable, right? So you can solve this particular problem easily, the data that is being given over here. Is it clear? So right, so let's take another example over here. So a 10% sodium hydroxide solution concentrated to 40% sodium hydroxide by evaporating water. So here we have to understand whether this problem is solvable or not, and in order to understand that, I have already told you, you calculate degree of freedom, right? So first, if you see the evaporation unit, right? So in evaporation unit, basically there will be a feed, right? And then there will be your water evaporated, and then the product that you are getting. So here water, that is product as feed, and I'll write feed as F. So what you see here, if you do the total mass balance, right? So F will be equals to W plus P. This will be your equation first. Second thing is that since only water is getting evaporated, so if you do apply balance for NaOH, because NaOH is constant, the quantity of NaOH will be constant, only water is getting evaporated, and due to this reason, what is happening, the concentration of NaOH is increasing from 10 to 40%. So what we can do, that apply NaOH balance, and here NaOH called as the tie component, right? If you remember my last lecture, there I have discussed about the tie component. So I can write sodium hydroxide in, that is equals to sodium hydroxide out. Sodium hydroxide in, that is equals to sodium hydroxide out, right? So here you can see there is equation first, there is equation second, right? Now I'll define variables. if you define variables, the variables are feed, water and product. So here you can see number of equals to how much 3 and how much number of equation we have got as 2. So what will be the degree of freedom here? That is equals to 3 minus 2, that is equals to 1. And if it is greater than 0, right? So what we have seen here, the degree of freedom is greater than 0, then you require one more information, right? So you required at least one more information. If 3 equation would be there, then that would be fine. So here you need, I think what I understand here, if I give you the total number of feed or how much feed is being supplied over here, then you would be able to solve this particular problem, right? So you have to understand the feed basis. So if you take 100 moles or 100 kilomoles of feed or something like that, then you will solve this equation, right? So right now this system is called a under defined system, where you require some amount of feed to solve this kind of problem. Is that clear? Right. Now here I'll be talking about steps for solving the material balance problem. It's a very important concept also. Right. So we can summarize the various points that we made earlier into the following steps by for the solution of material balance problem. So first step that I'll write, so read the entire problem carefully. Second will be draw a sketch for the unit. Why this is important? It will help you to understand the problem, because I have if you remember this, I have drawn the evaporator unit, like there was feed, there was product, then there is water evaporated. So here you can see this schematics will it will be very easy for you to understand, okay, this is feed, this is all of these things that is related to our particular problem, right? Now step third will be, so label the flow of each streams and associated component with symbol. So what I have told you earlier, we will write F, W, P and all. So you have to label, right? So better label the flow of each streams and associated composition symbols, right? Already I have explained it to you. Now fourth is list all the variables available data. Data on composition, right? Fifth, you can establish the key component or tie component. So there I have told you NaOH was the tie component, right? So this is very important. Establish the tie component, okay? After sixth step would be, so with the chosen basis, it's very important. With the chosen basis, write the overall material balance right? And then we'll solve the equation. The equation that you got, if it is linear equation, then you can solve using Cramer's rule or matrix method, or in Python, or analytically, whatever the thing that you are able to solve. And then you check the answer by substituting them. Right? That's great. So here I am going to solve one problem, and you will see how we can solve this kind of problem. I mean, in this lecture I'll stop here only. In the next lecture I'll solve one problem based on the material balance, and the step that I have described here I'll be using exactly the similar step, and you will find that these are the steps that is very important whenever you are solving the problem of material balance. This will help you a lot. Okay, thank you all. Stay tuned with the lecture. In every subsequent lecture you will be learning something good about the material balance, and after completing this course I am damn sure about that this course will be one of the easiest course for your chemical engineering. And this is not only a course, but if we talk about the mass transfer, heat transfer, or fluid mechanics, chemical reaction engineering and all. So if your material balance or if your process calculation is good, then another subject would be also very, very easy for you. Okay, thank you all for attending the lecture. Stay tuned. Thank you.